All right, this is section 15.4, calculating enthalpy change. You're going to learn about Hess's law and use that to calculate enthalpy change for a reaction. We're going to explain the basis for the table of standard enthalpies of formation. We're going to calculate the enthalpies of a reaction using thermochemical equations. Determine the enthalpy change for a reaction using standard enthalpies of formation of data. And an allotrope is one or more forms of the element with a different structure and properties when they're in the same state. So that's like the most common allotrope we know is carbon. Carbon is known as graphite, as a kind of a powdery thing of coal when it's kind of crystallized, and of course diamonds when it's, those are all allotropes. Hess's law and standard enthalpy heat of formation is what we're going to study here. Enthalpy change for a reaction can be calculated using Hess's law. Okay, so we're going to figure out what Hess's law is and use that to calculate the change of enthalpy. Hess's law states that if you can add two or more thermochemical equations to produce a final equation for a reaction, then the sum of the enthalpy changes for the individual reactions is the enthalpy change for the final reaction. So if we have like a two-step chemical process, is mostly what we use this for. We have one chemical reaction that produces something, then we use that product to produce, combine with something else to produce another product. The sum of those enthalpy changes for the individual reactions is the enthalpy change for the final reaction, where we started off and where we ended up. Okay, so the synthesis of sulfur trioxide. Okay, so we start off here with sulfur and oxygen. Combine those together to make two sulfur dioxides. Okay, so far so good. So that's our first reaction. Then we take the sulfur dioxide, combine it with oxygen again, and make sulfur trioxide. So the enthalpy change for the first reaction was, since it was negative, it gave off heat to do that, was 594. Then for the second reaction is 198. So we overall energy change from when we started off to where we ended up was 792. So that's Hess's law. So we can just add up these individual reactions and get our overall energy change. So how much heat was given up in the whole process? Well, almost 600 here, almost 200 here, for almost 800 overall. Okay, there's a bunch of standard enthalpy heat of formation is defined as the enthalpy that accompanies the formation of 1 mole of the compound in its standard state from elements in their standard state. So if we have standard states are mostly what they are at STP. Elements in their standard states have 0 enthalpy. That's just by definition. Okay, so we start off with 0 when they're in their standard states. Then we form compounds that are formed or placed above or below elements in their standard states. So it looks like this. We have the standard states of nitrogen, oxygen, and sulfur. Okay, so if we want to make NO2, we had to go up, right? We had to, went this way, we had to add heat to make that happen. And to make this reaction happen here, the other reaction, the SO3, it gave up heat when it formed those bonds. But the standard states were here, so comparing it to the standard states to get the nitrogen oxide and the sulfur trioxide, gave off heat, took heat. So the standard enthalpies of formation can be used to calculate the enthalpies for many reactions under standard conditions by using Hess's law. So we would just add up everything, all the individual reactions, to get what the heat of the overall reaction was. So the heat of the reaction equals the heat, equal this little m, kind of sideways m here is the summation symbol from math, equals the heat of the products minus the heat of the reactants, the sum of the heat of the reactants and the sum of the heat of the products. Okay, so here's some standard formations for Okay, sorry about that. Little pause there. The standard enthalpy of heat of formation. Here's some standard numbers, a chart you could use if you're dealing with these reactions. So these would just be for a reference, and they kind of use a little different chemical symbols here. They use like the halves to get the right number for half a mole, half a mole. That's something we don't normally see in a balanced chemical equation. So it works, but it's a little different than what we normally see. Okay, so that actually was about it for the video, so I could have just stopped it if I remembered that. All right, so answer questions, and I'll see you guys in class tomorrow.